Alright, so we've got a 2 kilogram mass that has been raised from rest to a height of 4 meters in 2 seconds, then released. So our object, which is initially down here, is raised up 4 meters in 2 seconds. At that point there, it's going to be released, so it's going to go up and then travel down, back down to the ground. So if we look at our first question, we're going to be determining the force applied to it. So force is equal to mass times acceleration. We don't have an acceleration, but we do have a displacement in a period of time. So that means we need to use our equations of motion. So for A, we're going to say that our displacement is going to be equal to ut plus half at squared. Our initial velocity is 0. So that means that our displacement is going to be equal to a half at squared, and that gives us our acceleration is going to be equal to 2 times our displacement divided by t squared, which is then going to be equal to 2 times 4 divided by 2 squared, which is going to come out as being 2.0 meters per second squared. That gives us our acceleration. Now we just need to go and do our force. So force is equal to mass times acceleration, which is just going to be our 2 kilograms times by our 2 meters per second squared, which is then going to get us our 4.0 newtons. For B is our power calculation. So we're just going to say that power is equal to the work divided by time. We could also use a velocity calculation, and it should be the same. So we know what the force is now, so this is going to be equal to our force times the displacement divided by time, which is then going to be equal to our 4 newtons times by our 4 meters divided by our 2 seconds, which is then going to get us our 8 watts of power. So for C, we want to find the final velocity. So C, I'm going to use equations of motion. So I can go v squared is equal to u squared plus 2as. We know that the initial velocity is 0. So therefore our v squared is then going to be equal to 2as. That means our v is going to be equal to the square root of 2 times our acceleration times by our displacement, which is then going to be equal to the square root of 2 times 2 times 4, which is coming out to be 4 meters per second. The maximum height of the mass. So if it leaves the top here with 4 meters per second, that means it's going to go up to a certain point. That point there is our total height. So we need to find out how high it's going to go. I don't have time in this situation. What I do have is the final velocity, right? The final velocity is going to be when it reaches the top. So I'm going to use 2as. Our initial velocity is 4 meters per second. Our final velocity is going to be 0 when it reaches the top. So 0 is going to be equal to our u squared plus 2as. S is then going to be equal to minus u squared on 2a, which is then going to be equal to minus our 4 squared divided by 2 times of our gravity, which is negative 10. So this is going to get our value of 0.8 meters. This is the point where it releases. So that is this part on our diagram. It's found that height, so that part there is where its velocity will be going to 0. So that value in there is our 0.8 meters. So therefore, the total distance above the ground would be equal to 4.8 meters. Now let's find E. So E is determine the energy as it passes downwards 2 meters above the launch height. So we're looking at a point, let's say here, this is 2 meters above the launch height. When we look at this one, we want to think about conservation of energy. So the maximum amount of energy that we're going to have is when it's right at the top. This is going to be our potential energy in that situation, which is going to be equal to mgh. At the very top, we have our 2 kilogram mass times by gravity times by our height, which is going to be 4.8. That will give us 96 joules. It just so happens that at any point from the very top to the very bottom, energy is going to be conserved. So if I was to choose that point, or that point, or that point, or that point, as we move down, the total amount of energy at any of those points is going to be equal to 96 joules. Energy is conserved, energy is not being lost in any of these situations, so therefore, it's going to be some component of potential and some component of kinetic energy. So therefore, energy at 2 meters above launch point is equal to 96 joules. It's not the same on the way up, mainly because on the way up, we are doing work on the system. So there will be a different amount of work on this side of our launch. Work is being done to the object as it moves up. While it's having work done to it, it is changing the amount of energy. So therefore, we are adding energy into the system on that side. If we want to find the velocity as it passes downwards, so for part F, we know that the energy at any point is going to be equal to its maximum energy. So mgh is our maximum amount of energy when h is at the very top. That is going to be equal to its kinetic and potential energy. So this is going to be equal to mgh at our point plus its kinetic energy, so half mv squared. Masses is going to cancel, or we could leave mass in, mainly because we've got a value for our maximum amount of energy. So we could leave that in, otherwise I'm just going to do it all algebraically. We're solving for velocity in this situation, so our masses are going to cancel. We're going to have g outside of height at the top minus the height at some point is going to be equal to our half v squared. So that means our velocity is then going to be equal to the square root of 2g times by our difference in height. So our height at the top minus the height at some point. And that is going to get us the square root of 2 times 10 outside of our 4.8 minus our 2 meters above the launch height, which should get us the value of 7.5 meters per second. Now we're going to do the same thing for g. So g, we're going to find the final velocity of it. That means all of the energy has gone and become kinetic energy, and there's going to be no potential energy. mgh is then going to be equal to a half mv squared. That means that our v is going to be equal to, very similar to what we had before, it's going to be 2gh because we have no height in between. So that is just going to be giving us the square root of 2 times 10 times the 4.8, which is going to get us the 9.8 meters per second. Now for part H, this is rather interesting. We're thinking about how different components are going to be changed due to the resistance involved. So if wind resistance or some sort of drag is going to be included, it's going to oppose both the upward motion and the downward fall as well. That means that to move 4 meters in 2 seconds, we would actually need to increase the amount of force provided. If we increase the amount of force provided, the displacement and the time is the same, so that means our work is going to increase. The final velocity, though, is going to be the same, mainly because we've achieved the 4 meters in 2 seconds. We just oppose the work. So that one is actually going to be remaining the same. The maximum height, after it leaves the work being done up, it will actually have work done to it, which is going to slow it down. So therefore, our maximum height decreases. And that means that the energy at the top and any point below that must also decrease. So that means that any velocity and any total amount of energy must also be less than what has been determined previously. Because work has been done by air resistance, so some of that energy has been used up on the way down.